So now we're going to talk about failure theories. And, this is pretty useful if we're going to predict how something's going to fail and if it's going to fail under some loading. So, when you're designing something and you want to be able to tell, is it going to withstand whatever conditions I'm going to put it in, right? And so some of the places you'll see this is like, so if you have a very expensive part, like basically you can only make it once, right? So I can't just test it under my predicted loading and see if it's going to break. Or if you have like a standardized part and you want to be able to just like give like general specifications, what you might do is something like a tensile test. You'll get like a sort of like test material and then you put it under loading until it breaks. And in general, there's like 4 failure theories that we're going to look at, 2 for ductile materials and 2 for brittle. So if you remember, the difference is that ductile materials are going to have yielding. So if you look at like that stress strain curve, right? So this is strain, this is stress. It goes like here, you have your linear region, then you have your elastic region. But the yielding, basically, it has some lengthening that'll occur before it fractures, whereas a brittle material is basically going to fracture without lengthening much. So it's the difference between like, if you have like a piece of taffy and I heat it up, I can stretch it versus like a hard one where it's just going to snap. So first we're going to look at the ductile materials. And in general, the way you can think about these, so we're going to have the shear stress one, and then we're also going to have it's called the distortion energy, or von Mises. And the idea is that, so if you imagine like a fish in the ocean, right? So all of this water has hydrostatic pressure, which means that there's a pressure that's equal in every direction on this fish, right? And it's really high pressure, like when you get deep into the ocean. But the reason that the fish doesn't just like get eviscerated is because it's in all directions. So it's basically uniformly being compressed so that it would want to, like, if it would actually get compressed, it would basically just shrink, right? And the reason it doesn't do that is because it has like equalized pressure on the inside and outside, and there's like evolutionary adaptations and all that. But that's the idea, is that if this is going to break, it's going to be from something that is not hydrostatic, not acting. It's not like hydrostatic stress acting in all directions. So this one, the shear stress, also called the Tresca, is going to say, okay, well, let's just look at the maximum shear on this thing. And then distortion energy, we'll get into that later. It's going to use basically this idea of looking at all of the energy that this material is absorbing under that loading minus the hydrostatic. So first, this is Tresca. Let me just put that here, Tresca. We know that it's going to want to fail in shear. So we could say basically this is the diagram that's going to go along with this. So if we have one of our principal stresses and the other principal stress, this is basically the state of stress if we looked at our little like stress cube or stress element, right? Where we have the maximum in one direction, this is like sigma P1, and then here we'd have sigma P2. So if sigma P1 gets above the yield stress, so some like right here, a bare sigma yielding, then it's going to fail. Or if sigma P2 gets there, or if the difference between them gets above that yielding stress and they have different signs, right? So if you imagine our like shear, normal stress, Mohr circle that we were talking about, if they're both positive and one of these goes above the maximum, or if one of them is positive and one of them is negative, but the difference between them is greater than the maximum, then we're going to say that there's failure. So basically, if any point on this if any point on these axes represents a stress state, if I'm outside of this shape, then I'm going to have failure. So real quick, just writing this out, we have basically if sigma P1 and sigma P2 are positive, then it'll occur if sigma P1 is greater than or equal to our yielding, or sigma P2 is greater than or equal to our yielding. And then the second case is that if sigma P1 is positive and sigma P2 is negative, then we'll have that it's going to fail if sigma P1 minus sigma P2 is greater than or equal to our yield stress. So the second theory is a little bit more complicated. We're looking at the energy absorbed by our material that causes distortion, not just hydrostatic like compression or tension. So the first thing we're going to do is we're going to look at the energy, which we're just going to call W because it's kind of like work if you think back to like Phys 1. It's equal to the integral of our force across our displacement. So we're just going to call our displacement delta because it's like the same right? But delta is usually what we refer to in solid mechanics because that's like our deformation. That's how much it's moved. So like if I apply a force P right here and then it moves this much, right? This is my delta. That's the same as my displacement. So we're going to call this force, and then we'll have differential delta. This will go from 0 to, we'll just call this delta final. All right. Now we're going to go ahead and rewrite our force as our normal stress times our cross-sectional area. And then our deformation is the same thing as our length times our strain. So we go and we plug these in, we're going to get that W is equal to integral of sigma A, and then we're going to do L differential strain. And I know it can be swapped around the differentials here, but this is a small slice of displacement, right? And this is a small slice of strain, and the only difference is that factor of the length. So these are going to be the same differentials. We'll just now be integrating from 0 up to our final strain value. And now we're going to assume that we're within the linear region. So we're going to use Hooke's law. So if you remember, we have like here, we're in the linear region, and then it goes like this. So in the linear region right here, this is strain and this is stress. We have a slope right here. It's called the modulus elasticity, or Young's modulus. It's the E is equal to my stress over my strain. So if I solve for strain, I get the strain is equal to sigma over E. So if I go ahead and plug this in right here, we're now going to shift from a differential strain to a differential stress that's being felt within the material. So this is going to be equal to integral of AL over E sigma d sigma from 0 to our final stress. And now I can pull out all of these right here because it's going to be constant with respect to my stress. So I'm going to get that this is equal to AL over E integral of sigma d sigma, that's terrible, sigma final from 0. And then this is going to equal, if we go ahead and we evaluate this integral, we'll get AL sigma final squared over 2E, and this is equal to the work. And now what we're going to do is we're going to normalize this with respect to the volume. Because if you imagine like I have some massive chunk of material, right, this is going to be able to handle more distortion, be able to absorb more energy than just a little bit. So if we divide by the volume, we'll get something that's kind of comparable between materials. And since, if you notice right here, we just have cross-sectional area times length, dividing by the volume is as simple as just dropping these terms. So this right here is our energy absorbed per unit volume, lowercase u, is equal to sigma, I'm going to drop the final here, sigma squared over 2e. And if we go ahead and we substitute in this right here, we also say this is equal to 1/2 sigma times epsilon. And now one thing to notice right here is if you look up here where we had like integral of sigma d epsilon, and then eventually we divide it by volume. So if you imagine if we just took out these terms right here, this integral was sigma d epsilon. And if you look at this graph right here, we have epsilon on the x-axis and sigma on the y-axis. So this integral right here is actually the same as the area under this curve. I don't think this is something over in solid mechanics, but like it gives you a pretty good intuition for like what's going on, and it's basically how much energy we're absorbing as we go across this curve, right? And since we assume that we are in the linear region right here, we basically have the area under this line right here, which is a triangle, right? So it'll look something like this. Well, this is our line, and then this will come down. So the horizontal length right here is epsilon, the vertical length is sigma. So the area is equal to 1/2 sigma times epsilon, which is exactly what we see right here. And even though we did this for normal stress loading, it's the exact same analysis for shear loading. The only difference is that, instead of normal stress sigma, we'll have a tau. Instead of normal strain, we'll have a shear strain. And instead of this modulus of elasticity, we'll have the shear modulus. But everything else should be exactly the same. So now what we're going to do is, instead of just having like a material that just has one load, like here, like this is my sigma P1, right, in the principal state, we're going to have all three axes. So we're going to have a principal in the other direction and a principal in this direction as well. And when we add up the energy absorbed by the material under all three of these loadings, it's just going to be the same as adding each of these up. So we'd say that our U, I'm going to say like U total is equal to 1/2, and then we'll have our principal stress and strain 1 plus 2 plus, and then our third one. And now what we want to do is we want to get rid of these epsilons, because usually what we're going to be given is just like the state of stress. So we're just going to have like our sigma P1, P2, P3. That's something we can calculate right? But we don't really want to have to deal with the strain. So in order to get rid of these, we're going to use the generalized Hooke's law. So if you remember, Hooke's law is just sigma is equal to E times epsilon, right? So I could also say that epsilon is equal to sigma over E. But because we're dealing with loading in all three directions, we're going to have to take into account the Poisson effect. So basically, if you remember, if I have like a box right here, right? And then I make this longer, like I apply some load, I put this thing in tension, it's going to get longer, but it's also going to get thinner. So like it's going to look like this when it's done. So you're going to have an axial strain this way, but then you're going to have a lateral strain in the opposite direction. And you're also going to have that in the third dimension. So basically we're going to have compression in the direction of into and out of the page as well. And Poisson's ratio is the ratio between these. So Poisson's ratio, Greek letter nu, is equal to negative epsilon lateral over epsilon axial. Or another way to say this is that our lateral strain is going to equal negative nu times our axial strain. And we're going to have these in both directions. So if we come down here and we want to write a strain as epsilon x, we'd have epsilon x is equal to, and then we'll have 1 over E, and then we'll have sigma x, which accounts for just the axial, and then we're going to have to subtract the lateral contribution from sigma y and sigma z. So this will be minus nu times sigma y plus sigma z. So just real quick, what we're saying here is that stress gives us equivalent strain, right? So our sigma x is going to give us just strain of the same sign in the x direction as well. And the fact the proportionality between stress and strain is 1 over E. So this 1 over E term is going to be here. But then this 1 over E term is also going to distribute to the stresses which contribute to strain from another dimension, right? So these are the stresses that are not in the x direction. So like here's my cube, right? I'm looking at, here's my loading that's just causing it to be strain, to be elongated in that x direction. But if I also have a stress that goes this way and a stress that goes this way, this is going to compress it in these directions, but it's going to elongate it in the x direction. So I do a minus, because if these are compressive, then it's going to make it longer in the x direction. Poisson's ratio, which converts between these lateral and longitudinal directions, or just these non-x-axis and the x-axis directions. And then I add each of these because they're going to have an equal contribution. And then the exact same thing follows for the y and z directions. We're just going to have that stress in the same direction and then subtract the stresses from the other two directions right here. So now what we can do is we can take all of these equations that we have right here and we can plug them in to our distortion energy equation right here, where I guess I should be clear that like x, y, and z are just some general axes, but that could also correspond to P1, P2, and P3, because there's nothing here that actually depends on a specific axis. The only thing that matters is that they're all mutually perpendicular, which they are, and then that this like x-axis, whichever strain direction we're looking at, is the same stress, is in the same direction as the stress, except for these two, which are going to be perpendicular. So basically, this x-axis could be any direction. So this could be our P1 direction. The only thing that matters is that this right here corresponds to this term. And then these terms correspond to perpendicular stresses, which is exactly what we have with this P1, P2, and P3. So we can go ahead and we can substitute these three equations into this equation right here. So just plug in right here, and right here. And when you simplify that, this is the equation that you're going to end up with. And it's kind of long, but it'll simplify out later. So at this point, we've written out the energy that's absorbed by this material under some loading conditions where these are our principal stresses, right? But we said earlier that we only want the distortion energy, right? Right here, distortion energy. So what we have to do is we have to take this U term and we have to subtract the component of it that's just from hydrostatic loading. So basically the picture to go along with this is we have our general state of principal stress, sigma P1, sigma P2, sigma P3, right? This is equal to some stress that's hydrostatic, it's equal in all directions, plus this is the stress that we think is actually going to lead to failure. This right here is the stress that's going to cause distortion energy. So this U right here corresponds to the energy absorbed under this entire loading right here. Now what we need to do is we need to subtract, well I guess first we need to find it, but then we'll subtract the U from this part right here. Now the way that we're going to do this is we're actually going to start by looking at just this distortion component. And basically the assumption that we're going to make is that the only change in volume that's coming on this element, or this just like differential component of stress, is going to be from this hydrostatic. It's either this hydrostatic component that's either going to make the volume increase or decrease. And this distortion component isn't going to change the volume, it's just going to change the shape. Then what we can say is, let's just label this like width, length, and height, and then it'll be a change, so we could just call it like our change in width, our change in length, and our change in height, right? So if our change in volume is equal to 0, then that implies that our width plus our change in width, so our final width times our final length times our final height minus our initial volume has to equal 0 as well. And now if you distribute all of these out, you're going to get a WLH term, which is going to cancel with this, and then the rest of it's going to look like this. And now I'm not really an expert in differential geometry or anything, but usually what we can say is that these differential terms that just have a single differential, right, are going to be much bigger than these double differential, like a differential times a differential, or like one where we have 3 of them, delta W times delta H times delta L, because this delta is already a really small value, right, and eventually we're going to take the limit as this delta goes to 0 kind of implicitly. So if we have a really, really small value times a really small value, then it's basically going to drop out and be negligible in terms of just these single differentials. So we're basically just going to get rid of this term, this term, this term, and this term right here. And now what we're going to do is we're going to divide both sides by WHL. So this is going to give us, this is going to be delta L over L plus, and then if we divide by WHL, we'll have an over H. So this will be delta H over H. And then over here we'll have a delta W over W. And this still has to equal 0. And this delta of a dimension divided by that dimension is the same thing as the strain. And when we if we take the limit as these deltas all go to 0, then it's just going to be the exact strain. So this is strain. I'm going to switch now from LHW to just our P1, P2, P3 directions, since we're eventually going to plug that in. So we have epsilon P1 plus epsilon P2 plus epsilon P3 has to equal 0. And remember, this is for the distortion component. All right, so now what we're going to do is we're just going to multiply both sides by E. So we can say that E times all of this also has to equal 0, because 0 times E is 0. And now what we're going to do is for each of these epsilons, we're going to use that generalized Hooke's law, where the epsilon in one direction is the stress in that direction minus, the Poisson's ratio times the stresses in the other directions. So if we go ahead and we take this and set it equal to that. So now look, for each of these 3 terms that are coming from this epsilon P1, P2, and P3, which remember is coming from the distortion stresses, which is why we have each of these minus P's coming in for where our stresses are. You can see we have a sigma P1, and then, so then out of this we can take that we'll have a sigma P1, sigma P2, sigma P3, and then a minus 3P. And then notice out of these new terms, we're going to have a negative 2 nu times each of our sigma P1, P2, and P3 as well, because each of these principles shows up twice across these 3. So we're going to have a 1 for all of these minus 2 times Poisson's ratio, and then this negative 2 times negative 3 is also going to account for the 2 plus 2 plus 2, which is going to give us 6 times P times nu out of here. So all of this can be factored up into this right here. And if we say that's equal to 0, we can just divide out this term right here. And then if I add across my P and divide by 3, I can solve for my P, which has to equal 1/3 times the sum of my principal stresses. So now coming back up here, when we wanted to get the distortion energy from this hydrostatic, which we said up here is 1/2 times sigma times epsilon, we know that our sigma, our normal stress, is P, and then our epsilon in any of these directions is going to be, well, we'll have our 1 over E. We'll have a P minus nu, and then this will be time, and then this right here will be P plus P. So we'll have P minus 2 nu P with the 1 over E out front, or be our strain in each of those directions. So we can say that our distortion energy from the hydrostatic is equal to 3, because we'll have 1 in each of these directions, times 1/2 sigma epsilon from the hydrostatic, where a sigma right here is just equal to P. And then we just said that this is equal to, we'll just write 3P over 2, and then this will be times 1 over E times P minus 2 nu P, which we can say is equal to 3 halves times 1 minus 2 nu over E times P squared. And then coming back to where we just solved for P, we can plug in this 1/3 times the sum of our principal stresses. So this is equal to 3 halves times 1 minus 2 nu over E times 1 over 3 squared times sigma P1 plus sigma P2 plus sigma P3 squared. And if we simplify that, we're going to get that this is 1 minus 2 nu over 6E times the sum of each of our principal stresses, all squared. So now if we take the total energy under this loading, which is this long equation we have right here in like this maroon color, and we subtract the energy from the hydrostatic, this term right here, we take this term in pink and we subtract this term right here, what we get is that our distortion energy from the actual distortion, not just our hydrostatic component. So this blue distortion energy is going to be equal to 1 plus nu over 6E times sigma P1 minus sigma P2 squared. I'll just go ahead and write out the rest. So now the key insight here is that we're going to create a value of stress that's basically quote unquote responsible for this distortion energy. So you remember earlier we said that the distortion energy is equal to sigma squared over 2E, and that was just in the linear case, right, where we're looking at some force which is going to cause some internal stress, and then we get the distortion energy of all that. But basically we're going to find a sigma that generates a stress that corresponds to this distortion energy, which is what's going to be called our von Mises equivalent stress. So when we set these equal to each other, we can just cancel out this 2E and we'll just be left with the 3 in the denominator right here. Now to get our equivalent stress in terms of just this state of stress, the last thing we have to worry about is Poisson's ratio. And it turns out the Poisson's ratio, based on an assumption we made earlier, is equal to 0.5. So basically, because we assume there's no volume change for this distortion component, nu right here becomes 0.5. And I guess we can just go ahead and do a mini proof right here. So let's say I have some rod with a square cross section and it's got some length like this, but it'll generalize to any kind of component. But I'm just trying to give you some intuition to where this comes from. So we'll go ahead and call these side lengths of our square, we'll call them D and D, and then we'll call this whole length right here L. All right, so if our delta V is equal to 0, then we can say that our initial L d squared, which is equal to the initial volume, so L d squared, our initial volume, equals L final times D final squared. All right. Now, if you recall, strain is equal to deformation over length. So if we multiply this across, we get that our deformation is equal to epsilon times L. So if we want our final length, we just get our initial length plus delta, which is the same thing as L plus epsilon times L, which is the same thing as L times 1 plus epsilon. So sending that into this equation right here, we can say that L d squared equals L times 1 plus epsilon in the longitudinal direction times D times 1 plus epsilon in the D direction squared, which is equal to L times 1 plus epsilon L D squared times 1, and then we'll go ahead and factor out this right here. So we'll have 1 plus 2 epsilon D plus epsilon D squared. Notice that we can cancel an LD squared from both sides. We get an L and we get a D squared right here. And if we go ahead and we distribute this all the way across, we're going to get that 1 is equal to 1 plus 2 epsilon D plus epsilon D squared plus epsilon L plus 2 epsilon L epsilon D plus epsilon L epsilon D squared. And then we're going to do the same thing again. So if you remember, these strains are basically packaged up as a differential, a small deformation divided by a length. So we multiply these by each other, we're getting a very tiny amount times another very tiny amount. So again, we're just going to assume that it's negligible. This term, and this term go away. We can also subtract across the ones. So we can say that epsilon d is equal to negative 1/2 epsilon L. So now going back to the definition of Poisson's ratio, which is equal to negative epsilon d divided by epsilon L. But if we go ahead and we substitute this in right here, we'll have a negative in the numerator, negative 1/2 epsilon L over epsilon L. Negatives cancel, epsilon L's cancel, and we're just left with a 1/2. So coming back up here, we're going to have 1 plus a half, which is 1.5, divided by 3 means that this whole coefficient out front is just going to become 1/2. So our final kind of classic way you'll see this written out is that the von Mises equivalent stress squared is equal to 1/2 times the sum of the differences between these principal stresses squared. And so basically in terms of our failure theory, we're just going to let this equal sigma yielding. So basically if this von Mises equivalent stress is greater than yielding, then we're going to say that we have failure. In other words, our factor of safety is just going to be sigma yielding divided by our von Mises equivalent stress. And now going way back up here to our shear stress theory from earlier, it turns out that if you plot this right here, this equation, it's actually the equation of an ellipse. And it turns out that it intersects with this shape at each of these points right here. So if you want to kind of get a visualization for what shape it's saying our material will fail in, it's going to look something like this. And it turns out that this is actually a closer estimate to where these materials tend to fail. So basically, the shear stress or the Tresca theory is a little bit more conservative, and the von Mises is a little bit closer to the actual. When you get into like FEA or whatever, sometimes you'll be asked to do like one failure theory or the other. And I know there's some like things where companies are like, oh, we use Tresca, we use von Mises, we like this, whatever. It's like they're both commonly used failure theories. So now we can finally move on to the brittle material theories. And these are a lot easier because basically brittle materials, they kind of snap and it's basically right along like the normal line. So like if I'm doing my tension test, tension this way, it fails in normal. So the first failure theory is literally just like, does it reach the maximum normal stress? So basically if either of these principal stresses get above the maximum or in the negative direction, if any of them come outside of the square, then we're going to say it fails. And like experimentally, we know that like right around here and right around here it fails. So basically we take these data points and then we create a square of where we think it's going to fail. And this actually isn't a terrible estimate. I know we just spent like 2 pages deriving all of the von Mises stuff, but it's actually not that bad. But sometimes brittle materials will have this property where they'll be better in compression than tension. So like concrete is a really good example of this. It's really, really good at resisting compression failure, but then you can pull it apart with your own hands. So we have this Coulomb-Mohr brittle failure theory, which basically accounts for that fact by sort of distorting this so that it has a bigger region before it can fail in compression than from tension. And so if we go ahead and we write out like the specific conditions, basically this one's just going to fail if magnitude of sigma P1 is greater than like my yield, or magnitude of sigma P2 is greater than my yield. And basically your factor of safety is going to be whichever of these, so like sigma yield over sigma P1 or sigma yield over sigma P2, like whichever of these is closer to failure, so whichever of these is lower. And then for Coulomb-Mohr, you're going to have to look at the signs. So basically, if both stresses are positive, so both positive, then we're going to fail if sigma P1 is greater than sigma yielding, or sigma P2 is greater than sigma yielding. And again, you'd use the same kind of factor of safety method as this. If they're both negative, then it's going to be exactly the same, except now you're going to have the compressive. And it's actually, I don't think they call it yielding because brittle materials don't yield. They just completely fracture. So this wouldn't actually be called yield stress. It would be called like the ultimate strength. I think that's like UTS, ultimate tensile strength. And then here we'll have the same thing, where our ultimate tensile, but then we'll have compressive for negative, and then if they have a different sign. So this will be if sigma P1 is less than my compressive, or sigma P2 is less than my compressive, because my compressive will be negative. And then the last case is where you have different signs. So in this case, basically, it's just going to be if it's outside either of these lines right here. So sigma P1 over ultimate tensile minus sigma P2 over ultimate compressive is greater than or equal to 1, then you have failure, which means that the factor of safety is just going to equal 1 over all this stuff. So it's just going to be 1 over sigma P1 over my ultimate tensile minus sigma P2 over my ultimate compressive strength.